Every Huawei Ascend 910C accelerator that ships in 2026 carries a tower of memory, dies bonded to the face of its compute chip with sub-micron precision. That tower is roughly the size of a thumbnail. It contains thousands of vertical copper connections drilled through stacked silicon, and the machine that places it onto the chip does not exist inside China in production volume. One tool, one step, roughly 600,000 chips riding on it. The question this map answers is not whether Huawei can design a competitive artificial intelligence accelerator. The design work is done. The question is whether a single bottleneck in the memory layer quietly caps the real shipment count at a fraction of the announced figure before 2026 closes. A production target is a claim about a network's capacity. The 1.6 million figure Huawei has put into circulation is only as real as the narrowest wire that feeds it. This map traces that wire from the compute die down through the memory stack and into the bonding step where the network pinches. The shape of the supply web, not the ambition of the engineers, decides the outcome. The Ascend 910C compute die is where the trace starts, and it is also where the first surprise lands. This node is genuinely routed. SMIC, China's largest domestic chipmaker, prints the 910C compute die using a process it developed without extreme ultraviolet lithography. Extreme ultraviolet machines from ASML remain export-controlled to China, so SMIC built around that absence using deep ultraviolet tools and multiple patterning techniques, exposing the same layer of silicon several times with slight offsets to achieve feature sizes that would otherwise require the more advanced light source. The result is a process called N+2, and it is not leading edge by global standards, but it is functional and it is domestic. Think of it as routing city traffic across 3 smaller river crossings instead of one large bridge. Each crossing adds coordination cost and transfer time, but the city keeps moving. Huawei made the same routing decision in silicon, disaggregating the 910C into chiplets, spreading compute across multiple smaller dies rather than one large monolithic piece a leading-edge fab would print. The architecture is a workaround. It is also a real product. The 1.6 million total accelerator target breaks down, by Huawei's own reported planning figures, into roughly 600,000 910C flagships and a larger volume of other Ascend configurations. No independent verification of achieved yield or confirmed shipment rate exists yet. These are planning documents as reported by the industry press, not audited production data. But the compute die itself, on this evidence, is buildable in domestic volume. The wire continues past this node without pinching. Node. The Ascend 910C compute die at SMIC. Wire status. Wire already routed around the choke point. SMIC's deep ultraviolet-based process prints this die in domestic volume. The constraint this map is hunting does not live here. The wire continues from the compute die to the object it must be paired with, and this is where the trace changes character. Every high-end artificial intelligence accelerator requires high bandwidth memory. The reason is not subtle. The compute die can process data faster than conventional dynamic. Random access memory can deliver it, so the compute die starves. High bandwidth memory solves the starvation problem by stacking multiple dynamic random access memory dies vertically, connecting them with thousands of through-silicon vias, and placing the resulting tower directly on the package next to the compute die. The bandwidth gain is structural. Think of it as the difference between a city's standard water pressure and the output of a fire hose. You can run the city on standard pressure, but you cannot fight a serious fire with it. Substituting conventional memory for high bandwidth memory in an artificial intelligence accelerator is the same category of mismatch. The 910C needs its high bandwidth memory stack. There is no package architecture for this class of chip that routes around it. The wire for that stack traces to Changxin Memory Technologies, known in the industry as CXMT. The domestic supplier that reports suggest is the primary source for high-bandwidth memory equivalent stacks within China's supply web. Changxin Memory Technologies is producing what reports describe as HBM1E class stacks, which are roughly equivalent in architecture to a generation of high-bandwidth memory that was leading edge several years ago. Volume and yield figures are not publicly confirmed. What exists are analyst estimates and industry reporting, not audited production data. With that hedge in place, here is the arithmetic the map is built to read. Reports suggest Changxin Memory Technologies' total high-bandwidth memory output capacity for 2026 is in the range of roughly 2 million stacks. That number has circulated in public discourse as evidence that domestic supply can support the 910C ramp. The map shows it is not confirmation. It is a constraint in a reservoir's clothing. A reservoir that holds 2 million gallons sounds like abundance until you trace the pipes it must feed, the fields, the factory lines, the municipal draw. 2 million gallons becomes the number that shows you exactly where the system runs dry. Changxin Memory Technologies is not a dedicated 910C supplier. The broader Ascend product line draws from the same wire. Partner products draw from it. Any export-eligible configurations draw from it. Allocating 2 million stacks across a realistic product mix puts the 910C allocation somewhere between 250,000 and 300,000 packages. That is roughly 40 to 50% of the 600,000 flagship target. The headline and the arithmetic are not living in the same document. I want to be direct about what I think is being missed in public readings of the Changxin Memory Technologies capacity figure. The 2 million stack number is being quoted as though it validates the 910C goal. It does the opposite. The moment you divide that figure across the full product draw, the flagship allocation falls to roughly half. That is not a contested analytical judgment. It is arithmetic applied to reported inputs. The contested part is the input assumptions, particularly Changxin Memory Technologies' actual yield on high-bandwidth memory stacks, which is not publicly confirmed. If yield is lower than reports assume, the gap widens further. The wire is live. It is narrow. Node: CXMT, domestic high-bandwidth memory supply for the 910C. Wire status: bypass in development. No confirmed production yield at required volume. The wire exists, the capacity is partial, and the arithmetic delivers roughly half the stacks the flagship target requires. From the Changxin Memory Technologies constraint, the map follows 2 parallel wires Huawei has reportedly begun drawing itself. Industry reporting references internal memory development programs under the names HiBL and HiZQ, framed as efforts to reduce dependence on third-party dynamic random access memory suppliers. The framing matters enormously here. These are early-stage programs, not production pipelines. Reports suggest they exist. No confirmed volume shipment or yield benchmark has been published for either. To change the 2026 arithmetic, these programs would need to produce not just functional silicon, but high-bandwidth memory-compatible stacks at yield levels and volumes that could be integrated into the 910C packaging line within the year. The distance between those two states is the gap this segment is measuring. Engineers have identified a second river crossing and are surveying the route. The survey is real. The bridge is not. Traffic is still crossing the one narrow span from the previous node. There is a further detail the map requires. Even if HiBL or HiZQ produces qualified stacks on some future timeline, those stacks must still pass through the bonding step. Solving the memory supply question narrows the gap. it does not resolve the bonding bottleneck. Every domestic memory route, whether it runs through Changxin Memory Technologies or a future Huawei internal program, rejoins the wire at the same junction, node. Huawei internal high bandwidth memory development, the HiBL and HiZQ programs. Wire status: no domestic bypass confirmed at volume. The parallel routes are drawn on the map. They do not carry traffic on any timeline the 2026 target can use. Now the map reaches the junction where every wire in this network converges, and the trace slows down because this is the honest dead end. Thermo-Compression bonding is the step that joins the high bandwidth memory stack to the compute die inside the accelerator package. The stack is placed on the compute die at sub-micron precision, under carefully controlled heat and pressure, forming the electrical connections that give the accelerator its bandwidth. Every 910C unit, regardless of whether its memory stack comes from Changxin Memory Technologies or a future domestic source from Huawei's own programs, must pass through this step. There is no architecture for this class of artificial intelligence accelerator that bypasses it. It is a single junction box in the building's electrical system, and every circuit in the building routes through it. You can rewire any room you like. If the junction box cannot handle the load, the building does not light up. The tooling for high-volume thermo-compression bonding at the precision high-bandwidth memory requires is produced primarily by a small number of equipment suppliers outside China. The leading generation tools from companies including BASE and others have become subject to export restrictions. Chinese equipment makers have announced development programs for domestic alternatives, and names including CETC and affiliates of memory manufacturers appear in reporting on those efforts. But no confirmed production volume deployment of a domestically built thermo-compression bonder at high bandwidth memory class specifications has been reported. The precision required is not a single threshold to clear. It compounds across a full wafer of bond sites. Placement error that is acceptable at one bond site multiplies through the stack, and yield degradation at any point in the assembly propagates through the package. Equipment makers outside China have accumulated years of process knowledge that does not transfer through a specification sheet. I want to test the strongest counter case honestly, because China has closed equipment gaps that Western analysts called permanent. Certain etch tools, deposition systems, and inspection equipment now have credible domestic alternatives that did not exist a decade ago. The argument that thermo-compression bonding is categorically different from those cases rests on the precision tolerances involved. Sub-micron placement across a full wafer, at production volume, with yields that make the economics viable. Reports suggest trials of domestic bonding tools are underway. No confirmed production yield data is public. The gap between a development program and a production volume deployment with qualified yield is the gap the map is measuring, and that gap on a 2-year horizon is real even if it is not permanent on a 10-year horizon. The 2026 target does not have the runway to wait for closure. The wire reaches this junction and stops. The bonding node is the dead end with no detour on the timeline that matters. Not because a domestic solution is conceptually unreachable, but because the distance between where the development programs are now and where production volume with confirmed yield needs to be has not been covered, and the year closes before it is. 3 nodes, 1 routed, 1 partial, 1 stopped. The map now reads complete enough to give a verdict. The compute layer is genuinely domesticated. SMIC prints the 910C die. The workaround is real, and this wire carries traffic. The memory layer is partially domesticated and actively narrowing. Changxin Memory Technologies is producing stacks. The internal programs are in development, and the wire is live but delivers roughly half the volume the flagship target requires. The bonding layer is the junction where the count is decided, and it has no confirmed bypass. My plain call is this: the network does not close into self-sufficiency in 2026. It closes into something more specific. A partially domestic web that will ship real ascend accelerators, probably a meaningful number, just not the figure in the headline. What I think the industry is not reading correctly is what happens if Changxin Memory Technologies scales faster than current reports suggest. The pinch moves. It does not disappear. The bonding junction remains the constraint even if the memory supply grows, because every additional stack still passes through the same step with no confirmed domestic tooling. The 1.6 million figure is a planning claim about a network whose narrowest wire, by the map's own arithmetic, cannot carry it. That is not a verdict on Huawei's engineering. It is a description of the supply web's current shape. The high-bandwidth memory stack returns here as the object that rewrites the 7-figure headline. Not because it cannot be made inside China, but because the step that joins it to the compute die it must feed cannot yet be performed at the required scale with domestic tools. A single bonding junction, smaller than a postage stamp, is where the shape of this network decides the count. What changed in 2026 is not which accelerators are faster. What changed is which segments of the supply web are now domestic and which remain single points of foreign control. The map shows 3 nodes. One is routed. One is partial. One is not. The headline number lives at the intersection of all 3. The map is not complete because the network is not complete. It is complete enough to read where it pinches, and right now, it pinches at the bond. The question I am tracking for the next version of this map: if Changxin Memory Technologies scales high-bandwidth memory output faster than current reports suggest, and a domestic Thermo-Compression bonder reaches qualified yield even below best-in-class, which node closes first and in which quarter? Leave your read in the comments. The arithmetic will update when the capacity numbers do. If you want to follow the map as the nodes change, subscribe, and you will see the next version when the wire moves.